In this problem, you have Tarzan who's going to swing from a vine from a higher location than the ground, and he's going to swing down this vine, and at the bottom point, he's going to pass through and arc around up here. And the question or one of the questions is, if the maximum tension in the vine is 950 newtons, can he successfully swing without it breaking? So the concept behind this is that when Tarzan jumps from this cliff and is accelerated by gravity, there's going to be an extra force or extra tension on the string due to that. Basically, the tension is going to change its direction, so there's an extra pull on it. Is that force greater than 950? So uh, we need to find, does the string break? So in essence, this is actually a force problem. We need to find the force that acts on the vine at the bottom point. um, so we have a force problem, but there's actually an energy problem wrapped up in here as well. So I'm going to go off to the side here, and in the solution in your homework, you should have a force model type problem, because that's what it essentially is, but we'll see how energy plays in. So in the force model, the first thing I'm going to do is I'm going to draw an FPD, and this is going to be Tarzan here, and the forces that are acting on him are the tension pointing up, whatever that tension is, and the mg pointing down due to gravity, and that's it, those two forces. Um, and we're going to consider this a centripetal force problem because there's an arc here, circular arc. And so I'm going to sum the forces in the radial direction, and I'm going to put the center up top. The center, I'll call it C up there. That's the center of the arc, or the center of the circle. So the radial direction is going to be up, and I'm going to have a box equals mass times AC centripetal equals 0 equals mv squared over r. Specifically, it's vb squared at the bottom. So in the x direction, this direction here, I have box equals MAI equals box. So in the radial direction, I actually see two forces. I see a T, and I see minus mg. So the tension in the string is actually, if I look at this equation, and there are no forces here, and it is accelerating. In the radial direction, I see that tension is equal to, if I solve for T is equal to mg plus mv squared over r, mvb squared. So there's the tension is composed of two things, the weight itself, plus this extra force needed to uh, keep him in the circle of radius r when he's going velocity v. So this is where energy comes in. I know everything here except the velocity. So the question is, how do I find the velocity of b? Well, we have conservation of energy. The energy at A equals energy at B. If I draw my reference line, and I'll draw my reference line right here, the lowest point of the motion, right there, that's step one, draw my reference line. I can then look for the energies that exist. So at point A, he just jumps off, so initial velocity is 0. He is above the reference line, so we have some potential energy here. There's no springs involved. At the bottom, he has kinetic energy. And because I set the reference line at point B, there's no gravitational potential, no spring, and there's no mention of friction, so I can ignore that. So for the velocity, I can use conservation of energy. So my equation becomes mg h at A equals 1/2 v and 1/2 mvb squared. 1/2 mvb squared. Fix that a little bit. And so if I solve for VB here, if I solve for VB, I can then plug that VB back in there. Actually, I can just solve for VB squared and plug it back in there. Once I calculate the tension, then I can compare it to the original 950 to determine if the string will break. The later parts of the problem ask at what point will it break. So what you can do is use the same idea of a force model in combination with the energy model to find out when that happens. And I think part of the problem asks at what angle it occurs at. So if you know what height that occurs, let's say hypothetically, it's this height here, height at C, let's call it, or height max. Then for that given height, I can find out the theta that is by using some trigonometry. So that's the conservation of energy Tarzan problem.